So what we're going to do in this lab, you're going to be developing a model for the dynamics of this wheel. This wheel is made out of PVC. It's hollow inside, and then it has end caps on each end. The end caps then have a shaft that comes out with some bearings. So there's going to be some friction in these bearings. Friction is going to be one of the things you're going to add into your model to make it even better. So you'll have a dynamics model without friction, and then you'll also have a dynamics model that has a frictional torque that slows down that rotation due to the friction in those bearings. The reason why we have these training wheels coming out the back side is so that we can take our measurements of omega as the wheel rotates and rolls. In order to do that, we have to use the encoder, which is right here, this little black box. You might recognize this encoder. It's the exact same one you just got done using on the locomotive crank lab. So it works in the same way. So I believe you got a little bit of an introduction on that. You may have forgotten what was said. So let's kind of revisit how the encoder actually works. This is what it looks like. We have the data sheet if you're interested. It has a shaft that goes into a disc, and that disc has a series of slots around it. That gives us 500 different slots around the disc itself. Let me scroll down here. I also want to show you this tutorial. This gives a zoomed in picture of what's going on inside the encoder. So this disc that I mentioned has 2 rings of slots in that disc. There's a light source on one side that can shine light through these holes in the disc, and then a light sensor on the other side. So if there's a hole in the disc, then the light sensor reads that as a high pulse on the square wave, and if the light source is blocked, then that's the low part of the square wave. So as this wheel is rotating inside the encoder, as the shaft rotates and our entire wheel rotates with it, they all rotate as one piece, a square wave is sent out. There's actually 2 square waves. We have a channel A and a channel B. That's not really important for you for this lab. We use those 2 square waves if we want to determine direction. So if channel A is leading channel B, we know it's going one direction. If channel B is leading channel A, we know it's going the other direction. But for this, we don't care. We're only going to go one direction. We're going to take this wheel and we're going to roll it down a ramp. The ramp is actually set up upstairs, so we'll show you a video of what that looks like in a moment. And that's when you'll be doing your testing, because it's a lot more interesting to see this roll under the effect of gravity. Right now, it doesn't roll on its own. So, when we're rolling it down the ramp, we're not going to roll it backwards up the ramp. It's only going to go in one direction, so we're only going to need to use one channel from the encoder. We can ignore the other one. And then what we can do is we can count these pulses, and we can see how many pulses have passed per second. We have that calibrated so we know how much distance is traveled, and we can figure out how many radians per second of omega our wheel is rotating. Okay? So we can take that. We can also take that omega measurement and get theta from it by taking the derivative. I'm sorry, the integral. We can take the integral of that to get the position. So we'll get both position and omega, theta and omega, from this single square wave coming out of the encoder. Make sense? Any questions on that? Okay. So you're going to do 2 different cases of this wheel. You're going to do the dynamics of the wheel when it's in the balanced case. So the balanced case is what you have listed here, or shown here. The balanced case means that it has a constant inertia all the way around. So it's just going to roll nice down the ramp in a nice balanced fashion. Okay? In the other case, we're going to take and add a large point mass. So this rod is going to be your point mass that you can model as part of your dynamics equations that you're going to derive for this lab. And this point mass can be placed eccentrically about the radius of rotation of the wheel by placing it through this slot. So there's a hole that this goes into. Needs to feed through to the other side. Then there's a cotter pin to keep it in place. This cotter pin is extremely important that you put in place and have it locked. Otherwise, if the mass comes out during rotation, which has happened, then that mass will hit on the training wheel as it rotates around, and it will tear the training wheel, which is holding the encoder in place, and tear it off of the shaft. So it's very important you get that cotter pin secure. I can show you what that looks like from this side, since you can't really see that. So you make sure that's placed all the way in there so it can't slide out. Now this mass is going to want to dictate a different behavior of the rolling of the wheel. And when we take that and put it on a ramp, it's going to cause a really cool eccentric behavior, because that point mass, as it spins around, is going to accelerate and decelerate the wheel as it rolls down the ramp. So you'll see it speed up and slow down, speed up and slow down as it eventually rolls down the ramp. The training wheel itself is not going to factor much into your frictional torque. We've noticed over the years that it works better for our training wheel to actually just be a sliding mass. So don't be surprised that this wheel actually doesn't rotate. We have it locked down in place, so it just drags behind the large PVC wheel. It doesn't actually roll. And we've done that on purpose. In the past, when we had this loose, the wheel and the bracket would actually vibrate and cause more measurement issues, because then your entire encoder sensor that's tracking your omega is also vibrating and moving. So it caused a lot of problems. In terms of getting the data from the encoder, it's really a very simple system. Everything's run off of a small circuit board that powers off of a 9-volt battery. So make sure you have a good, fresh 9-volt battery. You can check it with the multimeter to make sure that the voltage is around nominal voltage for a 9-volt battery. If not, we have others that you can use. That just plugs into the case here, and then everything else is wirelessly transmitted. So those pulses from the encoder are being wirelessly transmitted over to our little box over here, which is receiving the signal from the encoder, and then passing it through this small data acquisition device. This data acquisition device, it's a USB 6008 is the number of it. That gets plugged into the computer. Right now I'm using the lab station computer so that you can see it on the projector. But when you go upstairs, you'll actually be just running this off of a laptop. So you can be right next to the ramp and get all of your data through the laptop. So the USB cable will just plug into the laptop. LabVIEW, same program I'll show you on here, is on the laptop, and you can save all of your data to the courses folder, which we have linked on this laptop as well. So everything can be done locally. Then all this device is doing is just taking and counting that square wave of pulses. Counting those pulses, sending them to the VI, and then letting the VI do the calculation for theta. So let's show you what the VI looks like next. Okay, really pretty simple. We have a plot on the top for theta, which we got as the from our omega measurement. So we had our radians per second. This is actually what's being calculated from the square wave of pulses. And then from that, we take the radians per second and integrate in order to get our position of theta. And we get both of those live on the plot. That's the only two pieces of information you need for this dynamics model. The rest of the information, the masses, the diameters, all of those things are in the lab document. So you can refer to that for the rest of the inputs for your model. We'll make sure with our lab assistants that our DAC is labeled the right device. This is just a helpful note for us so that the computer actually reads the proper device when displaying the data. And then we can go ahead and hit run in the top left corner to run the VI. It's not going to display anything until you start actually moving the encoder. So it's just waiting and sitting at 0. Now as I move the wheel, you'll see the radians per second move and the theta increase. Notice that if I go forward or backwards, it still counts that as an increase in theta. So it just keeps incrementing theta as it goes. Also notice as I go multiple rotations, it's just going to keep accumulating theta. So theta is the entire amount of radians that you've traveled. So you're going to need to unwrap that if you want to see how many rotations that was, based on your 2 pi radians per rotation. Okay? Then once you have your run down the ramp, you want to make sure that you start the VI first before you release the wheel. Also notice if you move the training wheel with respect to the PVC, that's also registered as movement. So the encoder doesn't know the difference between the movement of the blue wheel or the movement of the training wheel. It's measuring the relative movement between those two. So as it's rolling down the ramp, if this goes over a bump in the road, that bump in the road will be seen as error in your measurement. So take note of that as you're taking data. If you notice anything on the ramp, we've taken out the screws that are in the seam of the ramp so that you don't have those bumps in the road. And we've tried to make it as smooth as we can, but there might be occasions where you see that. So keep that in mind. You'll start the VI first before it can wait for you until you're ready to go. You can get everything set up. For the balanced case, you're going to be releasing it down the ramp. Also, it can go in either direction. It can either go this direction with the training wheel on this side, or it can go this direction. Doesn't matter. For the balanced case, you'll just be taking it, making sure that you use, I'll point this out in the video in a minute, make sure that you use the stops, the door stops, on both the front and the back of the wheel. Otherwise, the wheel will fall off the back of the ramp. And when that's happened in the past, it basically falls to the ground and rips the arms off. And then we have to repair it before we can do any more lab data. So don't let it fall off the ramp. You'll also need somebody to catch it at the other end of the ramp. So you'll have your team members, one to release it at the top of the ramp, one to catch it at the bottom. For the balanced case, it doesn't matter what the orientation is of the wheel when you release it. We do have a distance nominally that we're having you release it from. Those are marked with blue lines of tape. So there's a starting line and a stopping line, basically. That's the points where you want to take data. For the unbalanced case, that's when we have the mass installed like you see here. It really, really matters where you release this, because this mass is going to dictate how much initial energy it has to start down the ramp. So if I start with the wheel, with the mass at some angle, it's going to have more initial energy when it starts to rotate than if I release it from a lower angle. It's not going to have nearly as much energy when it gets started down the ramp. So it does matter on the position of that angle. Thanks. So what you want to do is you want to release the wheel when it's in the unbalanced configuration when this mass is perpendicular to the ramp. So imagine my ramp is at about 8 degrees. I want to make sure that my mass is perpendicular to my ramp. And then it's right at that tipping point where it's going to want to tip and roll down the ramp. And you get the maximum amount of energy and the most effect from that eccentric load. Any questions about that? Okay. Let's go ahead and show, one last thing I should mention. Make sure at the end of your data run that you stop and save data. Do not use the red stop sign at the top. Can you move that dialog box out of the way for just a second? See this red stop sign? Don't ever, 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 ever use that red stop sign. That's an abort button. That aborts the VI in the middle of whatever it's doing, and that can put it into an undefined state. So we don't use the abort button. We want to stop our program in a nice and controlled fashion. So we use the stop and save data button to let the program finish its while loop, finish its last calculation, and then write all the data to the data file. So very important difference between those two buttons. So you'll use the stop and save data button. That'll bring up this dialog box. And then navigate to the course folder. We have some folders that Chris has been so nice to set up for you. In the 2003 folder, under the unbalanced wheel, group save data here. And inside there, there's already folders for each of the different sections and groups. We're going to be taking groups in pairs. So groups 1 and 2 will go and take data together. You'll share your data just between you two groups, and then you'll write your reports separately. And then we'll do the same thing for the rest of the pairs of groups. You're going to be taking 2 data files for each case. So 2 data files of the balanced, where the mass is removed, and 2 data files where the mass is installed for the eccentric loading. It's very different on the screen. You'll get to see a very different behavior, and I'll let you wait to see that in the lab. We won't show you that here. We'll leave you something to get to explore. There are some sample data files already available. So if you want to get started on the derivation and looking at the data files, the sample data here from previous trials is there, so you can start coding and deriving and doing this lab before you even get a chance to test. And then once you do test, you only need to analyze your 4 data files. These sample data files are just to get you started. So don't worry about those for the report. Does that make sense? Okay. Lastly, let's show those videos. So there's the setup that I was talking about, where you want to make sure that the mass is nice and perpendicular to the ramp. So make sure you use your angle bracket for that. This is the balanced case, rolling down, and after it gets past the blue stop line, you can stop the rolling of the ramp. And there's a foam mat to help cushion it, but I prefer that it not roll off the end of the ramp, because that step at the end is pretty hard on it, and it could bend or damage the shafts. All right, and then we'll also show the setup for the unbalanced case, which is really the most important for getting that mass in the right position. Notice that we use the door stops both before and after to make sure that that wheel doesn't roll off the back of the ramp, because that's about a 2-foot drop, or down the ramp before you're ready to release it. Then once you're ready to release it, same thing, let it roll down. It's a little bit harder to catch because it's a lot heavier. The best way to catch it is with the rims. So these rims right here make a really easy way to catch it on each side as you're catching it when it comes down the ramp. Also, don't pick up the wheel from the training wheel. This is not a handle. It's not meant to be used to pick up the wheel. It's far too heavy for this small shaft. That will bend and break. So if you need to pick up the wheel, pick it up from the rims like that.